Properties of DFT. Periodicity. Due to the periodicity of Wn, both DFT and its inverse are periodic in frequency and time intervals of capital N, respectively. Here you see the meaning of periodicity in time domain and frequency domain, or DFT. Linearity. Both are linear. A1 x1 of n plus A2 x of 2 will lead to A1 x1 of k plus A2 x2 of k. Right. Circular shift. A delay of m samples in the time domain corresponds to the DFT multiplication of the original signal by Wn km. Since the sequence is periodic, its delayed version also has n samples that are transmitted circularly. Here you see whatever we said in the sentence. Proposition 2.9. Checking circular shift. If x of n is equal to x0, x1, x2, x3, then xn minus 1 will appear as x3. Just here assume that x3 has rotated and come to be the first sample, x3, then the rest, x0, x1, x2. If it was two shifts, suppose what would we have? Anyhow, x of k, without repeating this terms, now w for 1 times k times x of k, writing the relations, which will lead to DFT of x of n minus 1. Okay, very simple relation. Now the next topic, circular convolution against linear one. If we call the circular convolution of two signals, x1 of n and x2 of n, both with endpoints equal to x3 of n, then DFT of x3 of n, called capital X3 of k, with n samples or endpoints, will be equal to, here in time domain, the formula for convolution will lead to multiplication of their spectra or their DFT. Okay. In general, let the lengths of the two signals x1 and x2 be equal to n1 and n2 respectively. To have the same results for linear and circular convolutions, n2 minus 1, 0 should be added to the end of the sequence x1 of n, and also n1 minus 1, 0 to the end of the second one, x2. This technique is called zero padding. Therefore, the lengths of both sequences after zero padding will be equal to n being equal to n1 plus n2 minus 1. Okay? Please remember it. In this case, the answer to the circular convolution is equal to linear convolution. Okay? Since it's assumed that both sequences are periodic with period n, therefore the convolution will be circular, and the convolution of two sequences in the time domain is synonymous with their DFT multiplications. Okay, again, we have repeated the idea. Right. The index of n in H of n minus L represents modular shift or circular shift. if we consider the augmented zeros for two sequences so that their lengths be equal, then the circular convolution becomes linear. Here you see the illustration of the idea. We generate a new sequence instead of x of n. Okay, x3 of n will be x of n plus some zeros. You see here the length of the zeros. Therefore, x3 of k will be dft of x3 of n, and the length will be nx plus nh minus 1. And the same idea for h3, okay? And having h3 of k, no. Capital Y3 of k will be multiplication of x3 and h3. And in time domain, inverse dft will be y3 of n. No. Here you see the idea. The input x of n with a length of nx, zero padding with nh minus 1, doing dft with the new length, and in parallel, h of n with the length of nh, zero padding, doing dft with the similar length, multiplication, and then inverse dft and yn. This yn, circular convolution, the result will be similar to linear convolution. Right. Now, run a program in Python showing the result for linear convolution as well as the wrong and correct results for circular convolution with and without zero padding, where both sequences are assumed to be the test pattern 1, 2, 3, 4. Okay, let's run the program inside Python. Convolution. Now, here the results. The first one, x of n, h of n. The result from linear convolution is denoted as y linear n, 1, 4, 10, 20, 25, 24, 16. The wrong answer obtained anything. Here you see, please consider the length of the output, but correct answer y circular correct after zero padding will be the same as linear 1, 1, 4, 4, and the rest. Okay, going back to lecture note. Here you see the same coding. Now, run a program in Python showing the result for linear and circular convolutions for another sequences. It's not necessary to have both signals be the same. No, here x of n is 1 and 0.8 and h of n minus 10, 1 up to 8 and h of n minus 10 minus 11 minus 12. Okay, convolution 2. X of n, h of n, y linear, and the same results obtained by circular method. Okay. Again, the code. You will have access to code, so we don't want to waste time and making the video lengthy. Now, if the lengths of the two signals are long in time domain. That's a very important problem in real applications. Again, if the lengths of the two signals are long in time domain, provided that these lengths are a multiple of 2, then the operation based on FFT will be too much faster than the operation based on linear convolution. Okay. So, having important relations again, n will be nx plus nh minus 1, the length of x input, the length of impulse response, nh. Okay, if we choose n as a multiple of 2, means n being 2 to the power of 2, okay, n of FFT, of course, right. We will run FFT1. Now here you see elapsed time for linear convolution will be, say it, 0.17. Elapsed time for circular convolution or using FFT will be 0.018. And the ratio is 9.4. Significant reduction of computation time. Okay. Again, the code. Now, take home. Having x1 of n being equal to e to the power of j 2 pi n over m times a pulse with a duration you see here. It's a pulse, u of n minus u of n minus m over 2. And again the same. Okay, so it's a time windowed version of this signal, which is an exponential. Okay. And assuming that m be even number, find x of 1 being equal to x1 of n convolved with x2 of n. Write a Python program for it. The next question. Assuming x of n being equal to cosine of pi n over 2, again another pulse, you see here the duration, and h of n being equal to 0.5 to the power of n, again multiplied by a time window. Find x of k and h of k with n equals to 8. Then obtain y of k. Next, find y of n using inverse TFT. In the next step, check all the answers with n being equal to 15. Compare and analyze these answers with y of n obtained from linear convolution. Write a Python coding for it. The next topic. Modulation. The multiplication of two time sequences is synonymous with their DFT convolution, which in practice is called frequency modulation, or ASK, amplitude shift keying. You have had it in digital communications course. Anyhow, x3 multiplication of two signals in time domain leading to convolution, cyclic or circular convolution. Now, symmetry and antisymmetry in DFT. The real part of x of capital N minus k will be equal to real part of x of k, but imaginary part will be minus. Im x n minus k will be minus Im x of k, imaginary part or image. DFT of an even signal. If the signal in time domain is even, then DFT will have only real parts having relation with cosine. Okay? And similar topic about odd signal, which will have sine part. Right. DFT of a real-time domain signal. If the signal in time domain is real, what will be its DFT? The magnitude as well as the real part of the DFT of a real sequence is even. Okay, even. And its phase, also imaginary part, will be odd. Parseval theorem. The total power in time and frequency domains are equal. No generation of energy or power. Okay, in time domain, in frequency domain, or DFT. Very simple equation. The next topic is completely important. Leakage, windowing, and loss of resolution. The concept of windowing is that a signal with a time range from minus infinity up to plus infinity be considered within the period of time Wn time window. Wn happens from 0 up to capital N minus 1 and 0 elsewhere or otherwise. So the idea will be practical because we cannot compute anything from minus infinity up to plus infinity. So the realization using a time window will be assured. Okay, anyhow. So this is a time window. We will have xn of e to the power of j omega, or xn of omega will be equal to sigma n from minus up to plus infinity Wn times x of n, both multiplied by e to the power of minus j omega n. For example, suppose x of n is as follows, a cosine. Here you see the DFT, 2 Diracs times 2 pi ck's, c1, c minus 1, both 1 over 2, times 2 pi, and in continuous format. It's Dirac and shifted Diracs. Okay, for a period. And this period repeats. Okay. Now, xn of e to the power of j omega will be pi times capital W shifted. Okay, where W is DFT of Wn. Here we alias sync. Okay. So windowing is clear up to now. What about loss of resolution? It means that the function delta of omega minus omega naught will be spread as much as the main lobe, which is equal to 2 over n. Okay? Instead of having impulse Dirac, we will have a main lobe. A further explanation is that we expected the spectrum of a digital cosine to be 2 impulses because theory demands it. But in practical environment, we will have another signal. Okay, again, cosine to be 2 impulses at corresponding frequencies, periodic with a period of 2 pi. However, Due to the multiplication of cosine by a time window, we will witness the convolution of their spectra, and that's a very important result. And as a result, those impulses will appear as sinc. So we have lost resolution. What about leakage? It refers to the appearance of additional side lobes, which falsely indicates the presence of energy at frequencies other than omega 0. Okay. Here we have a very important illustration. Time sequence cosine, okay? W of n, you see here, from 0 up to, say it, some point 31 with a length of 32 samples. So the truncated xn from here up to here. No. Theoretical result apps of x, two impulses. The spectrum of W, here you see a sinc because a pulse in time domain will lead to a sinc in frequency domain, and of course it is periodic. Here we have shown only one period. Now, here you see the spectra of their resulted signal. Instead of having two impulses here, for cosine, we have sinc, leakage, loss of resolution, okay, loss of resolution, and that's it. Discrete cosine transform. It has a large applications in image compression, say it JPEG, or anything else which you will find it out. This time, instead of using DFT, we are using DCT, discrete cosine transform. It's formulated as follows. XDCT of K is equal to sigma n from 0 up to capital N minus 1 x of n times ck times cosine of 2n plus 1 times k times pi over 2n. Okay? Instead of having simple n, we will have 2n. It has meaning. And what about IDCT? So x of n can be constructed from xdct very simpler. 2 over n, again similar summation, this time with k. X dct of k, again ck, and the same cosine. What about ck? It's equal to 1 over square root of 2 if k is equal to 0, otherwise it's 1. Now, write a program in Python to illustrate the idea about DCT from scratch. Okay, let's find DCT. Here it is. Okay. The original signal, reconstructed signal from IDCT, which is called, denoted as x2 of n. We use NumPy and matplotlib. Sampling frequency is assumed to be 200, ts 1 over fs, duration 2 seconds. We find duration times fs as n samples. We define t and x as a cosine. XDCT Here the loop for computing XDCT, and here for IDCT, inverse discrete cosine transform. The same formula illustrated in lecture note and plot. Okay. Now, some questions for you. Modify the program so that the main program calls two separate functions for DCT and IDCT. So write DCT and IDCT as functions. Then confirm the correctness of the program's operation with other inputs. Add a section to the program to compare the original signal with the reconstructed signal from IDCT and declare whether or not their contents are equal. Write the inputs and outputs of the program into separate text and binary files for further investigations. So you will get familiar how to generate and write data into files as ASCII or text or binary files. Modify the program to work for a 2D matrix as well. Name some applications in which DCT is used. Provide similar topics for discrete sine transform, DST. And again, what's the applications and what's coding for it. So you have a very good task to get familiar with the ideas of signal processing and writing in Python. Of course, writing in Python, we prefer not to use a complicated libraries, just writing the codes from scratch. And that's the goal of this course. Now, another transform, discrete Hartley transform. Okay, xdht of k will be equal to summation from n equal from 0 up to capital N minus 1 x of n times, here you use two terms, cosine and sine. In DFT we had cosine plus j or minus j times sine, or e to the power of j blah blah. Okay, and the inverse Hartley x of n is equal to 1 over n sigma, the same sigma, but this time for k, xdht of k times similar operators. Moreover, we call cas of z being equal to cosine of z plus sine of z, which is equal to square root of 2 times cosine of z minus 0.24 times pi. So you may write a discrete Hartley transform using cas. Now, computing discrete Hartley transform and its inverse using DFT. We notice that xdht of k is equal to real part of DFT x of k minus imaginary part of x of k. Now in Python, writing a program to illustrate the idea. Okay, let me find it. Discrete Hartley transform. Right. And running the program. Process finished. No results appearing here. And the code here, we define DHT and inverse DHT. Or maybe here, if we show it, it will be clear. DHT, inverse DHT, sampling frequency 200 Hertz, having an input, say, in the form of a cosine, and again, loops for computing the equation as declared. And finally, having x3 as inverse DHT. Anyhow, you need to write and work on program to get familiar with the idea. No questions. Take home. Modify the above program so that the main program calls two separate functions for DHT and IDHT, then confirm the correctness of the program's operation with other input signals, add a section to the program to compare the original signal with the reconstructed one, and declare whether or not their contents are equal. Also compare x of n with x3 of n. Write the inputs and outputs of the program into separate text and binary files. Modify the program to work for a two-dimensional matrix as well. Okay? One dimension used in signal processing, 2D in image processing. Find some applications for DHT.